In a severe storm, tarps securing industrial cargo face extreme physical stress. Wind loads pull against anchors with over 500 pounds of constant tension. A failure at this scale is instantaneous. Within seconds, a torn tarp can result in thousands of dollars in ruined inventory, stalled logistics, and immediate danger to ground crews. Most postmortems of these failures focus on the vinyl. Because the fabric is what eventually shreds, it is commonly assumed that the material simply wasn't strong enough to handle the wind. In reality, the fabric is rarely the primary cause. The collapse begins at the microscopic interface where the metal hardware meets the fiber. Industrial tarp failures are often triggered by the standard metal grommet. These off-the-shelf components are not designed for high-stress industrial environments. Poorly engineered metal creates a stress hotspot. Instead of distributing force, it pinches the fabric, concentrating energy into a single sharp point. This transforms the metal into a cutting edge. Under high tension, the grommet slices through the industrial vinyl with almost no resistance. Once the initial fiber snaps, the failure propagates. Tension pulls the remaining material apart, leading to a massive, uncontainable structural tear across the entire tarp. Global shipping speeds are increasing, and cargo loads are heavier than they were a decade ago. These heightened tension requirements are exposing the limits of traditional fasteners, which were never designed to meet the rigors of modern logistics. When the physics of this tiny metal interface are ignored, the entire logistics chain is left with a predictable and catastrophic failure point. Examining a highly engineered brass eyelet at the microscopic level reveals the geometry required to prevent these failures. At this scale, a tarp's survival is a matter of microns. A variation of just 0.5 millimeters in metal thickness determines whether an eyelet maintains its grip or deforms into a sharp edge that destroys the fabric. This specific curvature, the perfect flange, distributes kinetic force across a wide plane of horizontal threads, preventing pinching. During high-pressure seating, the metal undergoes cold flow, flowing under extreme pressure without heat, directly into the fabric weave, locking the two materials together. This integration transforms the metal and vinyl into a unified structural composite. Rather than two parts acting against each other, they function as a single reinforced unit. True holding power is achieved through this seamless microscopic geometric integration, not through raw clamping force. Advanced polymers and carbon fiber define much of modern engineering, yet heavy industry still relies on a copper-zinc alloy like brass. The microscopic arrangement of crystals within a metal, its grain structure, explains how different materials handle industrial stress. Stainless steel has a hidden flaw. When subjected to the immense pressure of industrial stamping, its rigid crystalline lattice resists the change. This results in jagged, microscopic fractures that compromise the metal's integrity before it ever reaches the field. Brass, engineered with specific copper-zinc ratios, behaves differently under those same extreme manufacturing pressures. Brass possesses a self-healing grain structure. As the metal is compressed, the crystalline lattice shifts and sides, instantly reforming its internal bonds to maintain its strength without cracking. This flawless foundation prevents the catastrophic tear-outs that occur when more rigid, modern metals develop internal fractures during production. The safety of a fastener depends on its molecular resilience. A metal's ability to survive the manufacturing process perfectly intact determines its performance under a lifetime of heavy load. On a massive industrial site, these molecular advantages are what allow a tarp to hold firm against a raging storm. In high wind events, energy transfers directly into the hardware. Success depends on kinetic absorption, the ability of the material to take in that energy and safely dissipate it. This chart compares the kinetic load absorption of brass versus steel. The brass line curves gradually, staying safely below the failure threshold. Its molecular elasticity allows it to flex just enough to absorb the load without snapping. Rigid alternatives like stainless steel lack this ability. When the load hits the threshold, the metal cannot flex and fails instantly. The safety margin of an entire operation often rests on the integrity of its smallest components. The microscopic physics of a 50-cent fastener are what ultimately prevent a $50,000 logistical loss.